were fortunate to have a really nice diversity of team projects this year. The first one you saw, an artificial gravity space station in the low Earth orbit. Our second one now takes us out to the red planet, to Mars. So let me introduce our second team project, Marte.
Good morning, this is Gu from Viking News. A Marty spokesperson had made public their first mission to Mars. This is the first time that a crew of humans will land on the red planet. This is what he said.
Good morning. It's my pleasure today to announce the very first international human mission to Mars. It's been a very, very long time since we left the Earth and first stepped foot on the moon and began to look beyond and ask ourselves, what is the next destination? Well, now the next destination is upon us. And I'd like to announce the 4 crew members for that very first mission. Hanna Pettersson of Sweden, Josh Richards of Australia, Kartik Kumar of India, and Mariona Agosti of Spain. A great leader once said, "We do these things not because they are easy, but because they are hard." This will be a very hard and difficult mission. And this crew that we send to Mars will represent the best of the planet Earth, the best of our international, interdisciplinary, and intercultural peoples. We wish them Godspeed and good wishes as they represent all mankind on this initial voyage.
Hello, my name is Hannah, and I have been selected to be a part of the first crewed mission to Mars. Some might call me crazy, and some might call me brave. For me, it's just another step to learn more about our origin and our place in the universe, and to address the urge to always strive for more and to never be entirely satisfied about what we know. I want to help to push the boundaries of what we know even further. So, a man in the same situation as I am in now once said, "This is one small step for man, one giant leap for mankind." And I would say that going to Mars is probably the world record in long jump then, kind of, if you compare it to that. When I pass 255 kilometers beyond the surface of the moon, every second on our journey will be the furthest point away from Earth that any human has ever been. If that doesn't scare the living feces out of you, I don't think you are mentally stable enough for going on a mission like this. But being afraid is natural, because with fear comes curiosity, and with curiosity comes success. So, why do we want to go to Mars in the first place? Of course, there are scientific reasons. There is so much more to learn about this neighbor of ours. Has there ever been life there? Is there life there now? And can it host us in the future? How does microgravity affect our bodies? What kind of technologies do we need when I land on Mars? And how can we use that in everyday life on Mars and here on Earth as well? Advancements lead to economic growth, and that is benefits all of the society. This journey that I'm about to take is not possible without international collaboration. We are not doing this for national pride as we did in the space race. We are doing this because we as a species want to accomplish something together. And this far, it's going surprisingly well, actually. When I was a child, I had an amazing science teacher. He taught me more than just science. He taught me to believe in myself. And I think that all of us in here can relate to this, having role models that want us to step outside of our comfort zone in order to learn more about ourselves and the world around us. And I was fortunate enough to go to school in a time of new discoveries of Mars.
Hey, look. I managed to get a ticket for Starport 1.
Wow. Oh, hello there. Good morning, class. Welcome to today's lesson where we'll be talking about the new discoveries of Mars. Cool, right? Okay, so let's get started. To begin with, can one of you tell me a reason why do we want to go to Mars? Anyone? Jeremy?
I mean, it's not a question. I mean, everyone wants to go to Mars, and because it's super cool, yeah.
Yeah, you're right. It is super cool. Yeah, you're right. But another reason. Why do we want to go to Mars? More?
Maybe to find life there?
Spot on. That is the answer I was looking for. Very good, More. So, looking for life is one of the key drivers of a mission to Mars. So, to get things started, what might we be looking for if we are looking for life on Mars? Dina?
Water.
Right, again. Yeah, perfect. So, if we return to the Earth, on Earth, wherever we find liquid water, we almost always find life. Water really is the stuff of life. So it's pretty reasonable to say that if we can find water on Mars, or liquid water on Mars, there might be life there. Now, can one of you tell me something about the environment of Mars? So what about Mars means that we might not find water on the surface, per se? More?
Maybe because there is cold temperature and low pressure?
Exactly, yeah. So the atmosphere of Mars is very thin, gives it a very low pressure, but also it's a really, really cold place. So whenever we get water there, it's either going to freeze or evaporate really quickly, so it's not really going to stick around for so long. So, do you have a question, Jeremy?
Yeah, I don't understand what you mean, because that's a long time we know that there is water on Mars, I mean, on the poles.
Huh? Okay, this is a good point. Maybe I got ahead of myself. Because we've known for many decades that there is water on Mars around about the polar regions. But in recent years, there have been many exciting new discoveries that tell us that there's in fact an abundance of water all around Mars, not just at the poles. So, any of you know what any of these new discoveries have been of water? Dina?
I think we saw some soil that is made of clay, and clay means that there was standing water in the past on Mars.
Perfect, very good. Okay, nice. And so if we say there was liquid water in the past in Mars, it's reason to say there's the potential for there to have been life in the past on Mars. So we've also had orbiters that have gone around the planet. They've been there, they've looked at Mars, they've spun around and taken a look at the surface. And what they've seen is that in craters, there's ice around about the mid-latitudes. Now, this is significant that there's water not just at the poles, because it is telling us that there is, in fact, an abundance of life, enough for water, but the locations of the water means that these locations are accessible for a human mission to the red planet. So, you know, the poles, they're great and all, there's exciting things there, but it's just a little bit too cold, a little bit too tricky to get there. So, moving on. Any other questions about water? Yes, Jeremy?
All about water, because I saw something. I mean, I'm not sure at all. I don't know. Yeah, if it's I saw that there are also traces. There might be traces of water on the craters. I mean, it was something called RSL. I don't know exactly what it means, but
okay, RSL. RSL is an interesting one. It's a point of great contention at the moment because it's not really that well understood. But to give just a simple explanation of what this is that we've seen from space images of Mars dark patches flowing down surfaces on Mars. Now, some say this could be liquid water, others say otherwise. In fact, there seems to be a paper published every other week saying something otherwise. But if it is evidence of liquid water on Mars today, it again reasons to stand that, hey, there might be life there today. Okay, so life. Okay, what else? What else can you tell about new discoveries on Mars that might give evidence of life? Dina.
I know there's organics in the atmosphere.
Okay, yeah.
Oh,
Oh, more?
my mama told me that. I know methane, maybe?
Okay. Your mum told you that?
Yes.
Oh, she must be very smart. Great.
Yes,
okay,
very
good.
smart.
Okay, yeah. So yeah, there have been observations of methane on Mars in recent years. So in 2003, methane was first spotted in the atmosphere of Mars by the Mars Express mission. This was a surprising result because people weren't sure if it was going to be there, but it caused it piqued such interest. We pointed some telescopes at Earth to Mars to see if they could see the same thing. And they did, and they were still curious about it. So they sent Curiosity to look at it. So the Curiosity rover, the Curiosity mission, tinkering away on the surface of Mars right now, has a special instrument that was designed to look for methane. And it's found it, in a level that's similar to what was seen by the Mars Express missions and the Earth-based observations. So what's most interesting about this is that it's not only a background level of methane, but it peaks, it fluctuates with time, on very short time scales. Yeah, interesting, yeah, science.
But that means that Mars is not dead. That means that Mars is active, doing things. I mean, because I know that on Earth, methane comes mostly from life, no?
Yeah, no, methane, you're right. So on Earth, about 90% of the methane in the atmosphere comes from life, biological sources, mostly cows. But on Mars, yeah, so what we know, we actually have a pretty good understanding. So you made this point about, is Mars dead or is it active or, alive? So, yeah. Atmospheric models tell us that methane in the atmosphere of Mars should last around about 300 years. But these variations, these peaks and fluctuations, they occur on much shorter timescales. So what it really is saying is that there's some unknown process currently happening on Mars right now that is, unexplainably putting methane into the atmosphere and taking it out. Wow. Yeah, right. Cool, science. Right. So, any idea where a potential source of methane, what might be putting methane into the atmosphere on Mars? Jeremy?
I know that on Earth, it's possible to have methane also thanks to magmatic activity. I mean, to volcanoes and all these cool things.
Okay, like geological processes?
Yeah.
Yeah, no, that's a point. So, yeah, like we said, 90% of the methane on Earth comes from living sources, but some does come from geological processes. Now, it's possible that the methane on Mars comes from these geological processes. But what do you know about volcanism on Mars? When did it last occur? More?
Maybe 10 million years ago?
Yeah, it's not been 10 million years. And if the lifetime of methane is 300 years, what's that about? Okay, next, we also know that from the Mars Odyssey mission that was specifically looking for hotspots on the surface of Mars, it couldn't see any. So we start to think that possibly hydrothermal processes and volcanic activity might not be the direct source of methane on Mars. There could be underground reservoirs somewhere, but it remains, we don't know about it. Okay, another potential source of methane in the atmosphere on Mars. More?
Maybe outside of the planet?
Outside of the planet?
Space.
Space methane.
Yes.
Yeah, cool. How cool is that? Okay. Again, yeah, another really plausible point. It's possible that comets and micrometeorites can come down and, break up in the surface from UV radiation or burn up in the atmosphere and release methane in the process. Yeah, cool. But this process, our models don't explain for the peaks and the variations, the short scale time changes we see in methane. So it's possible, but, what I'm leading to is, what's the third potential source? Dina?
Maybe there is life on Mars?
Maybe there is life on Mars. Wow, okay, yeah. Cool. Woo. Yeah, life. Good. So, yeah, maybe there's life on Mars. And just to kind of step forwards a bit, if we were to, looking for life is a key driver for missions to Mars, and maybe one day we'll send humans to the surface of the planet to look for life. Now, if we do that, let's think about another new discovery. What potential risks might there be to humans should they go to Mars? Jeremy? You don't know? All right. Okay.
I know.
Oh, more.
I know everything. Radiation.
Radiation, yes, radiation. Why? Why is there more radiation on Mars than there is on Earth? Jeremy?
That I know. Because on Earth, I know we are protected from radiation thanks to the magnetic field that is deviating dangerous particles.
Yeah, okay.
And also it's the atmosphere that is protecting us from the radiation.
Yeah.
Whereas on Mars, you don't have this. I mean, the atmosphere is very thin, and you have no global magnetic field.
Exactly. So it is thought that Mars maybe once had a global magnetic field, but it's believed that that was lost around 4 billion years ago. And when that was gone, the atmosphere was left exposed to the harmful solar wind, and it was stripped away, leaving a thin atmosphere with very little protection from radiation. So it is a harsh radiation environment. Jeremy?
But does that mean that if we send a crew to Mars, we have to live underground to be protected?
Yeah, well, you're right to be concerned, and that is a good solution. Yeah, we might need to live underground because, again, our little friend Curiosity, tinkering away on the red planet, has been measuring for the first time what the radiation dose is expected to be on the surface of Mars. And it's calculated from the data that's been produced that potentially life may be able to survive 5 meters under the ground. So yeah, maybe we want to live under the ground. Now, speaking again of the ground, can we think about another new discovery, something to do with the ground? Jeremy.
I saw that Camilo posted something on Facebook. I don't really understand, but it was something that sounds very dangerous given the name is something like perchlorate. And given this name, it should be very dangerous.
Yeah, very good. Very good. Have a perchlorate. But be careful, because it's mildly toxic. Yeah, so what we have seen is that there are perchlorates, these special molecules in the soil of Mars, and they are potentially mildly toxic to humans. Yes, Dina?
So let's go to another place on the planet.
Another place where there's not perchlorate?
Yeah.
Oh, okay. See, smart idea. But, there's a but, sorry. What we've seen on 2 separate missions that have gone to very different locations is that they've measured similar concentrations of perchlorate in the soil. So we first had Phoenix, that landed about here somewhere. And then we also had the soil measurements made by Curiosity in Gale Crater. Let's say it's around about here. So we don't know, but we can potentially infer that there might in fact be a global presence of perchlorate all around the planet. Now, this will be an issue for human missions should we go there because, of its mild toxicity. So that is something we need to, think about in the future.
I have a
You're looking
question.
concerned, yeah.
Yes. Maybe we can use it for something good.
Yeah? No, you're right. And that's actually, you're jumping ahead. I can see you've done your homework. You read ahead today. Very good. Maybe you'll be a teacher one day, Yeah.
Maybe.
So yeah, it's a good point. Maybe the things that harm us can also help us, because with the perchlorate, you're right. We look at the chemistry, we might be able to use it in our rocket fuel as oxidizer. And again, when we look at the chemistry, we think we might be able to break it down and release oxygen, air that we can breathe, survive on the planet to put in our habitats.
Wow, it's great.
It's great, yeah. Science. Cool. Yes. But okay, so let's say we're in our Mars habitat and we've got our air, we've got all our oxygen there. Why might we not want to have a habitat only with oxygen in the air that we breathe? 100% oxygen. Jeremy.
Yeah, I know. It's because it might be toxic if it's at too high pressure and only oxygen.
Yeah, no, this is something harmful to humans. Yeah, any other reasons why we don't want pure oxygen in our breathing habitats?
It's a fire hazard.
It is a fire hazard. Health and safety is important. Yeah, good. So, what's in the air that we breathe? More.
Nitrogen.
Nitrogen, yeah. Oh, God, you guys are good today, huh?
We have almost 80%.
Almost 80% on Earth, yeah. Okay, so this ties in nicely to my 5th and final new discovery, nitrates. Because we have also found in some locations on Mars there are nitrates in the soil. Oh, Jeremy, yes?
We were talking about nitrogen, not nitrates.
Okay, yeah, again, so there's a bit of chemistry, there's some more cool science involved. It's understood that we can take the nitrates, do some sort of clever rearranging of what we have and spell out nitrogen in the gas. But nitrogen could be sort of something we put in our habitats to breathe, to make the air more, not Earth-like, but more breathable. But at the same time, what else needs nitrates?
I know.
You know?
Yeah.
What's that?
It's plants.
Plants, yes, exactly. So the kind of, if we're going to think about us living on Mars, growing our own food on Mars, the plants that we grow are going to need nitrates. And if we have nitrates in the soil, what can we grow? Potatoes!
Yes, potatoes!
Cool, okay. So just to recap, we've sort of skipped ahead about 5 new discoveries. We know there's an abundance of water, variable methane, harmful radiation, a potentially global presence of perchlorates, and some really nice, useful nitrates. But let's just kind of think about the future slightly, because I see a lot of smart people here, and maybe one of you will be the first astronaut to go to Mars. Woo, yeah. No selfies in class, please. So we think about the lessons we learn on Mars might be applied to Earth. If we can learn to live more sustainably on Mars, we might be able to take those lessons and apply them on the Earth. It's good. We could save our planet and potentially change another planet. And but we need to think about why we want to do these things.
I have a question, Mr. Teacher.
Yes, more.
If we're going to find life on Mars,
Yes.
what we're going to do?
What are we going to do if we find life on Mars? I don't know. It's a tough question. It's a tough question. Because it's a question that's not only related to science and technology. In fact, a mission to Mars is not going to only be a question of science and technology. We need to think about ethics. We need to think about all the disciplines. Because if we find life on Mars, is Mars going to be us, or is it going to be for the Martians? Do we have a right to go and take this life, mess it around, put it under a microscope, and study it? We also talked about some of the risks associated with going to Mars. The radiation, the perchlorates. Is it ethical, to send someone to Mars if we know there's we might do some harm to them, if there's so many unknowns about the environment? So these are tough questions that are raised that need to be answered by you, the future generation. But I just want to finish the class on this note that if we go to Mars, it potentially might be our greatest achievement to date. So, yeah, how we do it is going to be really important. Class dismissed.
Yes, Mars! Woo!
Isn't that inspirational? Talking about new discoveries, I was very fortunate having him as a teacher. Us astronauts often have the luxury to inspire others. I'm always very happy when I get to talk to children, because I remember when I was younger, when I got to talk to astronauts. The sweet summer of 2016. Other things that have been inspirational to me personally is, of course, science fiction. We have a long list there: Star Wars, Star Trek. And one thing they all have in common is that they all talk about interplanetary life. In the near future, this will be more than just sci-fi for us. This is just a small step in a hopefully long Martian future. And maybe one day we can live on Mars as we live on Earth today. Even though the reason for going to Mars is clear for me, it is not clear for everyone. The questions that were raised during my science classes when I was a child were inspirational for me, but confusing to others. And not everyone sees the necessity of exploring other planets. And I have been in countless interviews where I have been asked challenging questions. And so has everyone working with this, because Mars exploration is groundbreaking and it is controversial. And because of that, we need to talk about implications to create a bigger picture of living on Mars in the future.
Good morning. This is Mary Mars from Viking News. Today we have with us Linda Dow, Chief Scientist from the newly announced mission to Mars, a martyr. Linda, welcome.
Hi, Mari. Thanks for having me.
Linda, we all know that Mars is a hostile, desolate, and frozen planet. So why are we wasting time and money trying to find life there? Meanwhile, we have so many pressing issues right here on our home planet, like famine, lack of access to healthcare, deficiencies in the education system, environmental crisis, war, and so many more concerns.
Well, Mari, let me take you back to 1969. We went to the moon, we explored the moon, and now we know lots about the moon. Now it is time to go to Mars, learn about Mars, and potentially stay on Mars. So humans, they have a natural tendency to explore and uncover many mysteries. And by going to Mars, we would be able to uncover a lot of mysteries. For example, the search for life on Mars is a huge driver for going there. And the reason it's so important now is because we have so many new discoveries, such as the presence of near-surface ice water and organics such as methane. And by knowing that water is a primary need to sustain life, as well as methane can come from biological...
So there is water in Mars?
Yes, there are. We have discovered water on Mars in many different forms. But we have also discovered organics on Mars. And the methane, for example, coming from biological origins, there is a possibility that life can exist on Mars or has existed on Mars.
Have we fully vetted the plans, missions, and procedures for such an endeavor? And if not, don't we risk sending a crew through years and years of training only to have them wave goodbye to their families, launch, travel for 7 months through the darkness of space, just so that they go to Mars and die? How many decades will you set back space exploration when this mission inevitably fails?
Okay, well, that's quite a question there. Mari, this is actually not a step back, but it is multiple steps forward. So, as we know, if we take the example of Mars, there are a lot of implications to the new discoveries where we can have a lot of advantages to both Earth and Mars. So we take, for example, the new discovery of water. We are able to use it for our consumption, so we can extract it. It would help us to sustain humans on the presence of the Martian surface. And then there's a whole new category of in situ resource utilization.
What is that?
So in situ resource utilization.
What does it mean?
Please let me finish. So in situ resource utilization, or ISRU, is just a technical term of utilizing the resources on Mars while we're there, rather than bringing the resources from Earth to Mars.
Can we really do that?
Yes, so I spoke about the example of using water to sustain human life, or using it for plants as well. We could also use the new discovery of nitrates on Mars to help aid in plant growth, as well as maintaining the atmosphere in the habitat modules. Or even we learned about the abundance of perchlorates on the Martian surface. And with that, we could use it to create oxygen for the atmosphere, or even for rocket fuel as well. Then, there is a whole new subject of space applications where we can actually use the residual crustal magnetism on
Residual crustal magnetism?
Yes.
What is that?
So the residual crustal magnetism, quite a unique term. So we know that Mars does not have a magnetic force around it to protect us from radiation. But we do know that there are localized sources of this force of magnetism on the surface of the Martian surface. So we call that the residual crustal magnetism. And we could use this, to help with navigation systems, but eventually we're going to have to use satellite navigation systems to help the astronauts.
Well,
yes.
What if the incompetence and clumsiness of the astronauts and the engineers involved in this ill-conceived mission kills any life that exists on Mars right now, or destroys evidence of past life? Or worse yet, what if the astronauts return to Earth carrying microorganisms that prove to be lethal to our own ecosystem here on Earth?
Mari, it is our number one concern to maintain crew health safety, and it is also our number one concern to maintain the safety of the planet. So with regards to this question, I mean, it's a huge concept of planetary protection. We have to make sure that any potential organisms that we find on Mars, that we don't destroy it. And we also have to make sure that we don't bring any organisms from Earth to contaminate Mars.
How do you do that? How?
Well, unfortunately, there are no current guidelines that are applicable to finding life outside of Earth. However, we are trying to control for the situation by not having human interactions in areas where we know that where we believe water to exist on Mars.
Not having human interactions?
Yeah, so we're trying to not send any non-sterilized probes there, for example. We're trying to do the best we can.
Okay, let's stick to the point. So basically, we all know, and looking at your latest press conferences from Amarte and publications,
Yes.
that you have found that the soil of Mars contains several dangerous substances, such as perchlorates. What right do you have to compromise the well-being of our astronauts by sending them to a place with so many dangers?
Well, you are correct that there are high levels of perchlorates on the Martian soil. And on one hand, this is bad for human health because it does interfere with the iodine uptake of the thyroid gland. However, we are trying to minimize this problem by having some countermeasures to it, such as having supplemental solutions.
Like?
Well, because perchlorates actually prevent iodine uptake, then we are actually able to supplement the astronauts with iodine pills, for example, to help mitigate that issue. And furthermore, perchlorates are not actually a totally bad thing. Like, we could use it to create oxygen in the atmosphere, or even rocket fuel. That's a good thing to use for perchlorates. So again, crew health and safety is our number one priority.
What analysis have you performed regarding radiation exposure, galactic cosmic rays, and coronal mass ejections? And what are the results? What do we know about the impact of radiation to humans right now?
So due to the thin atmosphere, due to the thin atmosphere on Mars and the residual crustal magnetism not being a sufficient radiation shield, that as we believe, the main sources of radiation that we should be concerned about are galactic cosmic rays and solar energetic particles. And even though we know more about the solar energetic particles than we do about the galactic cosmic rays, we have predicted that the total radiation exposure for 3 years missions on Mars will be 100 times more than spending 3 years on Earth, unfortunately. But again, even though radiation can cause severe diseases such as cardiovascular disease, genetic abnormalities, cancer.
So are we sending our astronauts to Mars just to get cancer?
No.
Is that what you're saying?
No. That's not what I'm trying to say. I am trying to say that even though radiation does increase the frequency of these, we are trying to prevent them by developing biological countermeasures to, for example, having flight suits prevent radiation. So a lot of research is going into this.
So a new mission was announced, and we are still talking about research, right?
Well, we want to have the best up-to-date research, so we are currently in research and development and testing out all the products to make sure that they are efficient and that they work before sending astronauts to Mars. We want to be very prepared.
And how do you expect to address any challenges posed by the lack of atmosphere on Mars? I mean, what if the life support system fail? Will you let all the astronauts die?
No, so we have spoken about ISRU. So there are many different applications and of the implications of ISRU. So one, there are nitrates to help with creating nitrogen for the atmosphere. There are perchlorates to help with creating oxygen for the air that we breathe. And there are also a lot of implications that we want to consider. For example, we're trying to use a closed-loop bioregenerative life support system.
What is that? What is that? What is it?
Yes, that is actually a really good question. So this life support system is kind of a integrated system using biological organisms, microorganisms, plants and animals to sustain human health through managing the airway, the air, atmosphere, the waste, and nutrients and things like that.
Does it really work?
Well, again, this is currently in research and development, but it has proven to be good results so far.
I see.
Yes.
Linda, it's not a secret. Actually, it's a common knowledge that such a mission would require a huge amount of money. So, considering the astronomical cost of funding such a mission, what can the taxpayers watching us right now expect as a return, technology transfer or otherwise?
Well, Mari, unfortunately, it's very difficult to predict the future economy. However, if you do think in a business and management perspective, a mission to Mars is sort of like a disruptive innovation idea. So a lot of different business plans, ideas, products and services can explode from just a mission to Mars.
Are you talking about businesses on Mars, or what is
Yes.
that?
Actually, a lot of businesses can actually decide, oh, hey, I want to establish some business on Mars to create some money and use the resources there. But we have to be very cautious about this because we want to make sure that each business has a certain allocation to the resources and not 100% of the resources just for that business, because then that would be very dangerous. But in terms of your question with the taxpayers, it has actually been researched that for every dollar spent by the taxpayers' money, there is a 3 times increased return in value to the taxpayers' pockets. So in a sense, it's good.
Does this money go really to the taxpayers' pockets? What happens to this money?
Well, the money will be distributed around the business, private sectors, and back towards the consumers' pockets. Buyers' pockets. Sellers' products. Sellers.
Okay. We know that the next step you want to take is terraforming Mars. However, considering the current environmental and conservation crisis here on our own planet, how will you ensure that the mistakes that were done in the past are not replicated all over again on Mars?
Okay, this is more of a question of within the humanities department that we are currently addressing. So in terms of terraforming, there are a lot of risks involved, and we want to make sure that we analyze all these risks before performing any actions on Mars. With regards to this, there are a lot of consequences that could be involved with terraforming, and we also do not know the timeline involved for it to actually occur. So it's still in the process of research for sure.
But what do you actually want to do?
Well, if we were to terraform Mars, for example, it would be very good to, for example, we could make the atmosphere thicker to help for human survivability on Mars. And if we are able to change the Martian environment in such a way for humans to survive, we could potentially transfer this information back on Earth to sustain Earth and deal with the environment crisis there. Or we can go forwards to look at other planets and try to make them habitable as well. So there are a lot of implications with regards to this.
Well, Linda, thank you for joining us today.
Thank you.
Please stay tuned to learn more about the progress of Marte. This is Mary Morse from Viking News. Have a great day. Well, I don't know.
Yeah, that was tough, wasn't it? The risks are enormous of going to Mars. There's no doubt there. And the questions that she asked, it's true to ask them. You have to ask these questions because they are not easy to answer. We can't take anything for granted. What if we actually don't succeed? I trust my team to death and beyond, literally. But there are things we cannot control. What if I never return home? And what if I never see my friends and family again? There are so many uncertainties. How do you even deal with this? I don't know. Even on the journey there are difficulties that we need to think about. We will see the Earth disappear as we get further and further away, and then nothing. For several months, we will have no fixed point. There will only be darkness and emptiness and exposure. We will have occasional contact with the Mission Control Center here on Earth, with an increasing time delay for every day. Then, after the void, a planet will appear seemingly out of nowhere. And what awaits us there? An environment that wants to kill us. I don't know how to deal with this. I'm feeling exhausted and tired.
Red soil everywhere. It is a hostile environment. Without the protection from the spacesuit and the modules, I'll be dead within minutes. If there was a solar flare during the journey, how would we survive? There are so many possible scenarios where something can go wrong, and we will never stand a chance. There's no air. Radiation destroys our bodies second by second. Toxic air. The reduced gravity weakens our bodies. Toxic soil. Toxic water. My body is weak. There are 5 of us, each as alone as the next one.
Hello, welcome everyone. Yes, friends, thanks for coming together. I hope you all know our beloved Hannah has been selected as the astronaut for the next mission to Mars. It's really a great moment for all of us. That's why we thought we should have fun together with Hannah, and we're not going to see her for a long time. So we definitely need to have good moments with her. And thanks for coming. And David, where is Hannah?
Oh, maybe she's sleeping?
Sleeping? Oh, no. More. Can you just go and bring your sister? I can find out and bring her to the table. Thank you. Yeah, Hannah is really going to be creating the history. Yes, and we're all proud of her. Definitely. Yes. Hannah, where are you? It's time. We need you. Hey, there she comes. Hannah. Hey. Guys. Congratulations. Please join us. Yeah, it's really a great moment for all of us, friends, our family, all together. And really, life is beautiful. And talking about life on Mars is more beautiful. And I just want to recall there's one team, Amate, which has a group of scientists from all over the world, across the countries, a typical international interdisciplinary style. They all came together for the discoveries which have been found, and there are new discoveries. If you look back in the last decade, many discoveries have shown the light, and this team has literally put everything together, then done research, and they are given clear recommendations on what is required to find life, beautiful life on Mars. Like, there are clear indicators. You can see the discovery of water. You can see at the polar caps, as well as in the equator zone, in different forms. That's a real indication of a life existed or maybe existing on Mars. And there are other indicators also, like your presence of methane phenomenon going on, coming into the atmosphere. There could be a biological source down beneath the surface. That's another indicator. Then you have organics, the carbon compounds. That's another indicator for life on Mars. So, Team Amate, as you know, as humans, generally, we are more interested on the origins of life than probably the life has started on Mars and then come to the Earth. So it's really worth to search for more life on Mars. So Team Amate has given clear recommendations, good recommendations in the science, like you need to look for more amount of the methane presence, then probably extract from that the existence of life. And the subsurface drilling is most importantly recommended by the Team Amate, where at the time water sources are found on the above surface, maybe down below 5 meters of the Mars surface. But if you drill some more and go deeper, deep surface drilling may reveal different forms of Earth different forms of life existed, and probably could even from liquid water also. And when I talk about liquid water, I really have one of my friend, Tobias. You are aware of him, right? You met him some time back. Yeah, and he has got real interest on the water sources, and he's going to tell something on real good effects of the water.
Yeah, Hannah, I was really worried about you going to Mars because, we need water, and there's not too much water on Mars because you are not landing at the poles where everyone knows there's a lot of ice at the poles. You're landing in the mid-latitudes. They look like a desert. It wasn't too long ago that we found out that in the mid-latitudes there's actually subsurface water in the form of ice. And back then we didn't know where that water actually was and how deep that water was. So the Team Amate actually recommended that we send a precursor mission that is mapping the subsurface water with a shallow ground-penetrating radar, so we know exactly how far you have to dig down in the ground to get that water. And that water is probably in the first couple of meters. So I think you're fine with water, because the water is really important for you. We need the water, we need the ice to extract water out of it. And you need that water not just as potable water, but also for your oxygen to breathe every day. And the water is also really important for the rocket fuel. So we want to have you back, Hannah. So we want to do electrolysis with the water to get hydrogen and oxygen out of the water and fuel your rocket so you can come back. Another thing that Team Amate recommended was technology demonstration missions. So we know how to do electrolysis and other techniques here on Earth, but you are on Mars. That's way different. So we wanted to make sure that you are safe, Hannah, and that the technologies are working on Mars. That's why we sent already ISU demonstration missions that have proven that we can do all of these tasks on Mars. But I think Damiana was really worried about something still.
Yeah, Anut, we are worried, but we know that Amate thought about everything for you. So give me a hug. Yeah, because your landing site will be exactly where there is the major concentration of nitrates. So you simply can take the soil, put it into the greenhouse, and if you're worried about perchlorates, you just have to put it in the water, and perchlorates will dissolve because they are salt. Then you can take it off, and you have a pure soil where you can cultivate whatever you want. You can have tomatoes, cucumber, and everything, and wine as well if you, if you're like me. So, in the water you will have perchlorates, but you don't have to throw it because you can put bacteria. There are more than 50 kinds of bacteria that you can put in, and from perchlorates you will have molecular oxygen, so you can breathe. And if you have a sufficient concentration of nitrates in the soil as well, you can put bacteria in the soil, another kind, to take nitrogen to breathe. So you can have in your habitat you will have pure. You will have the air that you have on Earth, and that's it. So good luck.
Hi, Hannah. I know you're very excited for the journey there, but I want to make sure that you find your way back as well. To find your way back, you're going to need a Mars ascent vehicle and a lot of fuel. For a typical Mars mission, 90% of the mass sent into low Earth orbit will be fuel. But we're going to reduce that mass and reduce the cost by using ISRU technology for your mission. We're going to use ISRU technology to make some liquid propellant for chemical propulsion. The main way that the Amarte team had recommended you to do this was through the combination of by using methane in the atmosphere along with other substances. I'm sure you're also excited to get into your new Martian home. Well, luckily for you, you're not going to be living in your small, cramped landing vehicle, because since you followed our recommendations, you're going to be living in inflatable structures and deployable modules, so you'll be able to move about as much as you want, and you'll even have your own greenhouse. So enjoy your mission.
Hey, Hannah. We've also been hoping that you're going to have a happy and healthy mission to Mars as well. So the Human Performance has made some recommendations in the past for you, and we're really happy to know that we've got these stuff sorted out for you. So for the perchlorates, for the water, because they'll be there on the Martian surface and they can interfere with your thyroid gland and its function, we've really been working hard on developing bioreduction techniques, so bacteria in the water that can help remove electrons from the perchlorate to make it not toxic for your system. So that's going to be really helpful for you while you're there, and mostly because the water is the highest contaminant where you're going to find the perchlorate the most. You can also get a little bit through the skin and the lungs, but it's a minor risk. Also, we've been working really hard for you for radiation control. So the galactic cosmic rays, the solar energetic particles, and the secondary radiations produced have in the past been the biggest issues and concerns for astronauts going to Mars. We've been doing a lot of research in this. We didn't know a lot about it before, but we've done some studies about how the radiation interacts, along with doing some material science research. We have been working on finding out what kind of shielding we can use for it, as well as considering the Martian regolith. Unfortunately, the Martian atmosphere doesn't provide a whole lot of protection, particularly from the galactic cosmic rays, but through our engineers and good hard work, we've been able to construct for you a habitat made out of a combination of Martian regolith, the rocks there, and some new material sciences that we've engineered to keep you safe and happy on your mission.
Yeah, well, Hannah, I think it's getting late, but just one thing to remember, and that is Mars has been in the collective imagination for thousands of years. And cultures all around the world have wondered about the mysteries of this place that soon will be unraveled, hopefully. And this comes with great challenge in science, technology, and eventually will have a great impact in our culture. It's an invitation to go to Mars, and we are very proud and happy that you're part of this amazing crew. So I would like to make a toast for Amarte.
Well, friends and family, Dad, Thank you so much. Okay, bye.
Thank you, everyone. We're going to open the curtains, get the projector up, and then take some questions on the stage. Yeah? Or just here? What do people prefer? Just here. Okay. Where's the microphone? Second microphone? Okay. Question?
All right, thanks, guys. An amazing, amazing bit of academic theater. Thank you. Okay, so the purpose of this team project was to look at the recent findings that we've learned about Mars over the past few years from the robotic missions and other investigations, and to make some determination about how that might affect future human missions for HANA. And so I guess since you guys have been studying this now for a few months, my question to you is, what do you see as the number one challenge for human missions to Mars?
Number one challenge, it's subjective depending on who you ask. So at the end of our report, I went around asking each discipline, we divided up into discipline research groups, what their number one discovery, implication and recommendation was. So for engineering, the most important discovery was the amount of water in the soil, and the implication is ISRU technology for that. And recommendations are to further test ISRU technology, for example. Anyone from science or Pell, other disciplines want to answer their main impact?
Well, for science, it's definitely the search for life. Due to the subsurface water that we have, for example, we want to dig down in the ground several meters to find that life. And we found that actually human missions are enhancing the science that we can do, because it's really difficult to have robots drilling more than 5 meters down.
Again, on looking for life, a big issue that is being faced currently by, I think, the PEL aspects, so that's the policy, economics, and law, is that of planetary protection. Because at the moment, where there are locations where there is water on Mars, we are unable to actually go there and properly investigate without the proper COSPAR implications in place, or the countermeasures taken so that we don't contaminate any life should it exist on Mars. So fixing that issue is another one.
Just a comment on water. So during the study with Amarte, we were basically looking at different reports like the MEPAG from NASA. And the main point that, so NASA studied a number of studies. That was a report that was released April this year. And they are basically looking at the different water reserves in Mars, being ice, phyllosilicates, sulfates, and the regolith, the soil itself. So they are actually looking at the different amounts of power required, the difficulties to transport and process the water. That is, of course, something that at the moment requires a lot of assumptions because there are a lot of unknowns. They are actually concluding in this report that glacial ice would be easier in terms of transport distance, but I mean, ourselves are not really, I couldn't say, we would just argue on that because we don't know whether the sulfate minerals and the phyllosilicate minerals are actually, so what we understand is that they're bound on rocks. So we are not sure that the actual conclusions based on assumptions are necessarily correct. So we need to do more work on that. We need to actually understand whether this is true, whether, and we need to find analogs here on Earth to do it.
Okay. Good presentation with a lot of content in there. It was very content rich. Question on two-part question. One, you mentioned ISRU a lot. Did you look at other technologies that might be long poles in terms of that need some development prior to the mission? I didn't hear a lot on that, so I was just curious if you covered that. Did you look at the moon as a ISRU demonstration? Was there any commonality there or not needed for Mars in your guys' opinion when you were looking at that? And then I guess the second part of the question, with the more findings of exoplanets and our sense that life may be ubiquitous in the universe, what happens if we find life before you get this mission going, since you leveraged a lot of the rationale for it? You mentioned a couple other areas about disruptive innovation and kind of the overall human quest. Did you have any more thoughts on that rationale side you could share? Thanks.
I'll start off with a bit about part one. So ISRU in particular, it's a large part of our project. Like, for example, it's in the objectives, so we focused a lot on ISRU. I know we did look at some other things that will need development, like habitats and greenhouses, plant growth and things. But we did focus a lot on that. In terms of testing it on the moon or elsewhere beforehand, we had a pretty hefty discussion about this, and in the end we decided it's very difficult to make a roadmap without saying go to the moon or go to an asteroid beforehand to test this technology. Instead of specifying a specific case, we just said this should be tested somewhere else, possibly the moon, possibly asteroids, possibly Deimos or Phobos, but we did not specify where. That is up to the reader's discretion.
To address your second question about what if we find life elsewhere before we go to Mars, that would be great, that would be interested, but we would still be interested in life on Mars because what we're really searching for is evidence of a second genesis of life. And so we know that Earth once was, Mars potentially was a place quite similar to the Earth. It offers it's a great platform to exercise, comparative science. So if we can see unique features, or if we discover life on Mars that's uniquely Martian, what does that mean for where life came from? And Mars is really the perfect place to answer that question. Not only is there life somewhere else, but what do we know about a second genesis?
And well, so far, Mars is a great trigger to start thinking about an ethical framework to deal with such a finding. For example, we have to deal with how do we value that potential life form. Are we going to value them as those life forms on Earth? In the case of simple bacteria, are we? I mean, ethics have a universality principle. So are we going to apply this to life forms in all places in our universe? If that's the case, why the bacteria in Mars has to be more important than bacteria on Earth? We don't care about the bacteria in our bathrooms, and so on. So we are considering the development of a critical framework to address this issue.
Okay. First of all, thanks for a very moving, very intense, very personal, but impressive presentation. Well done. My question goes into the direction of the international collaboration, which was shortly mentioned in the report. So it's easy to say, yes, everybody should play a role and everybody should join. So what can emerging space countries do to participate in this effort? What can be done on the ground? Analog research was already mentioned, but what can be done on the ground? So what can be done by emerging space nations in addition to the big players? What can be done by developing nations? How can we bring in everybody on the globe into that? And what can be done on the commercial side in addition to the big players?
Hello. Maybe I can start a few bit now about the international collaboration first, and then somebody else can add something. And we during our study that we have 6-7 disciplines studying in different areas. One of is a PEL group, and we are also discussed about the international cooperation drafting first version, second version. We talk about the international collaboration. The point is, the main point is, we think that going to Mars is a human flight. It's not the individual nations. That's our main point. And our recommendation that we should recommend the international collaboration for the Mars missions. That's main. And then, but we do have the challenges or issues for the international communication, especially in the emerging countries you mentioned, including China, India. But our roadmap and suggestion we used to be that we should involve as much as countries to involve with Mars for the several reasons. First of all, is a human mission. Second one is a budget consideration. That going to Mars is not cheap. It's difficult. We need a lot of funds. So what I think that what we talk about, we need to advocate the international cooperation. We also now consider how to remove any policy issues and other restrictions, constraints for this area. For example, we think that the multilateral cooperation is not only bilateral cooperation. So multilateral cooperation, we can involve ESA, we can CNES, and it's Russian Space Agency, Japan, India, China. So it makes life easier to go to Mars. That's the main point. But we didn't address too much in the final report for the reason that we don't want this too long for the report. That's one of the reasons. But the other is, maybe it's not so mature, or if we deliver that for this area, because they are, emerging countries still is a little bit sensitive topics on this. So not too much on the final version finally, but we do spend a lot of discussion on this. Yeah, something more.
Hi, I'm from Astronaut Center of China. So from now, I think we as you know, the main flight mission in China is space station. And from now, we finished our space station. Maybe the next important mission is Mars. So I think in the few years ago, we have trained several astronauts from Europe in China in our center. I think maybe we can make close cooperation to train astronauts. As you know, in this summer, we have sent our astronauts to Europe to engage in the cave training. So, and in the future, maybe more astronauts from all around the world can come to China to train together and make a great contribution to the Mars mission. Yeah.
But one more point, we do include the international budget for different agencies. That means that it's possibility that we involve a lot of international entities to this. But we did not. It's not enough to address on the policy or legal issue on that. But on the business issue, a lot of topics. Maybe something else. Somebody else.
On the private side, there is no market yet on Mars, but there are some initiatives like SpaceX, Mars One, who works on it. But it's most likely they will be funded or supported by space agencies. So for the moment, space agencies are the major contributors, financially speaking. And the idea to pave the way to Mars is to establish a complete economic system on LEO first, and then on the Moon, that could then support future mission to Mars, like telecommunication relays, cargo supply, etc. But it's long-term perspectives.
Thank you. I have a couple of questions, but excellent presentation, very creative. That was very impressive. So if you look at, for example, space station, it's very important for the academic and industrial aspects in terms of doing research in microgravity. And it's been getting a lot of results and feeding back to creating new value here on Earth. If you look at the Martian environment, would there be any advantages, for example, to the medical, pharmaceutical industry? Could you elucidate maybe some of that value?
Matt? Dr. Matt?
I didn't need that intro. Yeah, the aspects like pharmacokinetics, pharmacodynamics aren't well understood for medications in microgravity. We didn't really delve into, at least from a human health standpoint, what's being investigated in terms of pharmaceutical development in microgravity. Certainly there's questions about the left-handedness and right-handedness of certain molecules interacting with the body. Would that maybe be different if you were manufacturing it in the space environment? This report did not cover that material about what pharmaceutical companies are doing in terms of space-based research. Certainly an interesting prospect in the future, which could lead to potentially significant developments, certainly with the amount of biologic drugs that they're in development right now and the advancements that they're making there. There's a lot of, I would say, a lot of opportunity and open doors potentially for that. The main restriction is obviously going to be such issues such as space on board the space station for conducting that research, the materials required, and obviously funding issues, moving materials up and down. And maybe even more complicated issues such as like patent protection and ownership of those rights, or who gets the development. It's in a different area which is not bound by geographic borders, so how do you enforce those kind of issues? So there's probably a lot. That's probably certainly a PhD sounding topic in itself, potentially, but definitely, yeah, we didn't address it, but room for development. Was there anything else to your question which I didn't address, or?
No, that's exactly what I wanted. I have a second question. You guys talked a lot about agriculture and creating, using nitrates to enhance the growth of products there. So have you thought about waste agricultural products as a feedstock, maybe to create fuels and other energy sources?
We actually wanted to use the inedible biomass of the crops to make compost to enrich in nutrients the soil of Mars. And the same with human waste, of course, depured by the toxic elements. So this is our plan to make a good soil to cultivate any kind of crops. And did I answer? So the waste product to make fuel. Actually, to make fuel, we want to use a combination of perchlorates and ammonia and H3, which is a currently used propellant, and methane as well. You're welcome.
Okay. Can you comment on recent advances in trajectories to reach Mars, and whether you have any preferred option in your roadmap? For example, trajectory with minimizing the exposure to radiation.
So about 8 days ago, our report structure was a very different format. We had it laid out in a chronological way of like starting with preparation before your journey, the journey to Mars, landing on Mars, living on Mars, and leaving. Our internal review highlighted to us that that structure did not show, it wasn't clear how that structure met our objectives. And our objectives are about the new discoveries and the implications of them in the Martian environment. So despite myself having written about that, it didn't end up in the final report because we specifically chose not to cover the journey too. I can comment about it just based on my own research. It's not really part of the project, but if you want to talk after, I'm more than happy. Or now? So, yeah.
Yes, thank you. Thank you. I very much enjoyed the presentation. 2 questions. One, I did hear, and perhaps I misheard, some comment referring to the lack of maturity of planetary protection guidelines, and perhaps COSPAR hasn't done as much as some would like. But I know a number of agencies have been working on planetary protection for many years and have missions both on the drawing boards and have been conducting a lot of things. So did you look at what exists in other than what COSPAR is doing and make any judgment about the level of appropriateness and what needs to be done on planetary protection? That's the first question.
Policy, Economics and Law Department, we addressed this question, of course, because here we're talking about a human mission to Mars. And as for planetary protection agency level, planetary protection standards, the sole episode in the whole history when it actually was implemented is the Apollo program. Now with our new destination Mars, new questions arise because we have new data about the Martian environment, which implies that life might be present there. Planetary protection is still very restrictive on human and both human robotic missions because COSPAR basically sets uniform guidelines for both. And what NASA is doing right now, they are developing new agency level requirements for human missions specifically. But at this point, there are too many gaps remaining, and this is a work in progress, and perhaps COSPAR should relax its current regime, but this is a very tricky issue because we don't know what exists on Mars. We know how to prevent contamination, of course. That's what's been done with spacecraft, but not human missions necessarily. I referred to Apollo for the Apollo program, but gaps remain at this point.
Okay, thank you. Second, is there another
side comment on the pill?
Okay.
Yeah, this reminds me of a subject related to my research for the project, which is that any future mission is going to need a legal foundation like the International Space Station or CERN. And depending on the countries that want to join as members, or the space agencies that want to join in the membership of this foundation, their perspective on planetary protection could create conflicts. one country might be extremely convinced and persistent about certain planetary protection rules, such as using only areas for landing outside the Mars special regions. Other countries might disagree. Other nonprofits involved in the project might also disagree. And this poses a huge future challenge for the drafting of an agreement, which will form the foundation for this future agency working on the mission.
Do you have words along this line in the report, in the final report, that talk about the nuances, and not that it's just an easy problem to solve, but
Yeah, we have a discussion of different agencies and their activities around researching how we can. You wrote that section, so I won't.
Basically, yes, we have a whole section on planetary protection, and the overarching problem, in our view, is that the Outer Space Treaty system, especially Article 9, which sets two principles upon which COSPAR based its current policy. It's prevention of forward contamination and back contamination. For example, the Antarctic Treaty system, it's more flexible. So we are talking more in detail about the global level, that there is no consistency between what we will need in terms of planetary protection to actually send humans to Mars, to make their stay on Mars safe, and to make sure that we don't contaminate Earth, bringing something back we have no notion about. At the same time, speaking about potential life discovery on Mars, there are no guidelines on the international level defining what is the protocol if we encounter non-intelligent life, for example, there. It doesn't exist, so it's still... we made some recommendations in the report regarding that.
I'm just going to add something on the scientific point of view. We had very interesting conversation with Doug Archer from NASA about the scientific aspect of it. So we found that sometimes the rover missions in particular are finding themselves in this somewhat paradoxical position where they're either sent to region where which are not like these special regions where it's thought that it's very likely to find life, or if they're approaching these regions too much, they would be told to go away to somewhere else. And it's not only about it's not only about policy, and it's also from a scientific point of view very important that if you're about to make this paradigm shift that we found life somewhere else, you don't want to discover your own molecules and your own... So this is something I think many of us were surprised about, that very often rovers are looking for past life, or like for proof of life that used to be around, and not like current life. And there is a clear distinction between the rovers which are clean enough to look for life and rovers which are not. So that's the kind of science aspect of this problem.
And my follow-up question was, not follow-up, but a distinct question, is about the radiation issue and mitigation approaches for habitation on Mars. There was an ISU team project, SSP16, which was called Mars Caves, to look at the natural features on Mars and whether or not the habitation might be actually underground or in these caves as opposed to in habitats that we built on the surface. Did you make use of that information, and is there anything new in the discoveries about the radiation environment that would either conflict or either contradict or change any of those recommendations, and anything you've looked at?
I know that one key recommendation was to send a probe, a rover, into very low altitudes on Mars, say like in impact craters, because we believe that since the atmosphere is a lot denser and thicker at that point, that will provide improved radiation shielding. Another area that we looked into, slightly dead end, would I be correct in saying that, is crustal magnetism, and I will give you over to possibly the world expert on crustal magnetism at this stage.
This was a funny point in our project because I poured my heart into the research of residual crustal magnetism, hoping it would provide something in the means of radiation shielding, only to really be repeatedly told, nah, it's not really a thing. We can't do much with it. So there are strong regions of residual crustal magnetism on the surface in the southern hemisphere. These are curiously strong, but really not strong enough to provide protection or deflection from, space radiation. They also would only deflect charged particles, so if you have high-energy neutrons coming in, that's not really going to offer much shielding. But any shielding that is offered is going to be mitigated by the fact that in the southern hemisphere, where the magnetism is strongest in the crust, you're actually at a higher altitude. And this comes back to the point Harry was saying, where you have less protection from the atmosphere above. I know, we talked about the results from Curiosity, the measurements of radiation on the surface, and how we understand there could potentially be life around about 5 meters underground. And so to come back to your point, did we look into that? Potentially we could take soil and put it above our heads. But then again, we get into the messy realms of planetary protection, because once we go under the ground, we could contaminate the planet much to a higher degree. It's believed that if we send contaminants to the surface, the UV radiation environment will kill all sort of anything we take with us. But the second we start to go underground, there's we potentially risk contaminating it globally.
As you understood, I care about greenhouses. I love them. And plants don't need a particular protection toward radiation, except for the seeds responsible for the reproduction of plants. So if we want to go under the ground, we can leave the greenhouses in the surface.
Thank you for the nice presentation. And can you mention the different disciplines that you addressed in the project?
The disciplines we divided ourselves up into in the first couple of weeks were for research purposes, and that is space engineering, space applications, human performance in space, management and business, space sciences, policy, economics and law, and humanities. Yeah, got it all. 7 different research groups.
Okay. What is the length of the mission? Is it 1 year, 2 year, forever, or it's? And what's the size of the expedition? How many people?
This ties into the comment made earlier about we didn't want to go too much into mission planning. As far as I know it, there are, we could say 3 mission lengths. There is a short stay mission, about a 6 to 8 month journey to Mars, stay there for 30 days, and a roughly year-long mission back through the orbit of Venus. The second option is long stay, which is 6 to 8 months there, stay on Mars for 1.5 years, and 6 to 8 months back. And the third is permanent, no return journey. This also was a big discussion point at the very start of our project, because we thought that if you're staying there for 30 days, you can probably bring a lot of the supplies with you. You don't need to worry about spare parts. You could probably bring a lot of water, some fuel with you, and you don't have to give much thought into ISRU technology. Whereas if you're staying on the surface for 1.5 years, you definitely need to become at least slightly self-sufficient. So we discussed this a lot at the start because we needed to align our recommendations. In the end, we didn't decide on a specific case, although it was discussed in the report, because we didn't really want to. If we pick a specific case, it narrows our audience and it goes into more of a Mars mission design rather than new discoveries about Martian environment. I hope that answers your question.
Okay, thank you.
Only one small point that I added that with 7 disciplines, but more resources have been on engineering, science, and application. But there's only a couple of days from the PL or management. So we want to use this report to focus on technically and solutions, how to go to Mars.
Can I add something? For the long stay and for the very long stay, we thought about an habitat, which is a composition of modules. The first module is not human, so we'll go there and it will go there, and it will be completely autonomous, with a part made of greenhouses, and another part made dedicated to EVAs. And the second mission will be will be a module attached to the first module, and will be manned, and will be the habitat for astronauts. So like a living room and a bathroom and other facilities, and the whole structure will be one habitat, and they will have greenhouses as well. And if we want them to stay more, we can send other modules. So it is in the report if you want to go deep.
All right, thanks. So we've unfortunately reached the end of our question and answer time, and we have to allow the third TP some time to get set up for their presentation. But I'd like to thank you all again and have us all offer our applause. Team Mars.